Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is RIT 120 Hydraulics. Today we're going to finish our discussion of pressure control valves, and hopefully we're going to do this in one fell sweep while we knock out the counterbalance, the unloading valve, and the brake valve, three remaining pressure control valves we've yet to discuss. But before we do that, let's have ourselves a quick pop quiz. So this pop quiz is relatively easy. We've thus far discussed the pressure relief valve, the sequence valve, and the pressure reducing valve. Your job is to tell me which one they are, A, B, or C. So let's look for a pressure relief valve. Tell me which one it is. The sequence valve. Tell me which one it is. And the pressure reducing valve. Tell me which one it is. So our pressure relief valve. Let's start off with that first one. Pretty obviously, this guy. Your sequence valve is this guy. The only one that remains, pressure reducing valve, is B. So let's discuss each one in turn. First one is our pressure relief valve. Quite obviously, that's the pressure relief valve. Why? It's next to a pump. It's relatively close to the pump. It is normally closed. It's sensing pressure upstream. Why is C our sequence valve? C is our sequence valve because it is within the hydraulic circuit next to an actuator. And some of you guys might be saying, well, hey, how do I know that that's a sequence valve? Because there are no two cylinders that I'm trying to determine the sequence of it. Because again, the purpose of a sequence valve is to ensure operations in an orderly sequential manner. And my response to that is tough, because that's still a sequence valve, because it is normally closed. It's sensing pressure upstream. It is externally drained, and it has a check valve bypass, and it is located within the hydraulic circuit next to an actuator. And basically, it is not going to do anything. The cylinder will not extend until pressure at this inlet port overcomes a certain value set on the biasing spring, at which point the sequence valve will open up, and then the cylinder can extend. In reverse operation, when you want to retract this thing, this check valve bypass just ensures that it operates in a normal manner in reverse flow. Okay? So B is quite obviously our pressure reducing valve. Why is it a pressure reducing valve? Well, it's normally open, because all pressure reducing valves are normally open. It's sensing pressure at its outlet port, commonly called the R port. It has an external drain, and additionally, it is also check valve bypass. Because basically, as pressurized flow enters here, it's not going to go through the check valve, but it will go through the pressure reducing valve. At which point, it is sensing pressure on its outlet, i.e. R port, and if it exceeds a certain value, it will start closing. Okay, ensuring that the pressure at its outlet port remains or maintains the correct outlet pressure regardless of inlet pressure. The check valve bypass is for a case when you want to retract the cylinder. It's just ensuring normal operation in reverse. Okay, so hopefully you did pretty well on that pop quiz, identifying each one of the three valves we've thus far discussed. Let's go ahead and introduce the first of our three remaining valves, and that is namely the counterbalance valve. My question to you before beginning the counterbalance valve is, how do we control the speed of descent of a lifted object? So here is an incredibly large weight that we're lifted, and we want to go ahead and retract the cylinder. So your immediate answer should be, at this point, if you've not yet completed this lecture, well, probably a meter out flow arrangement, whereby when this is P and this is T, pressurized flow will enter here, start filling up this cap end, But the problem is if there wasn't a flow control valve here, this T-port basically has no pressure or incredibly low pressure, and it's not going to support that weight. So not only do you have the weight pushing down on this thing, you've got the pressurized flow pushing down on this thing, and this thing is not pushing up. So what happens? Well, that weight slams to the ground in an uncontrolled fashion. Very noisy, very dangerous. Obviously something you want to avoid. So that's why we do our flow control valves. What it's doing, the flow control valve, is limiting the speed at which the cap end, in this particular case, is drained. Because it can't go through the check valve here, it is forced to go through the flow control valve. Okay? So that's your immediate answer to, okay, how am I going to go ahead and control the descent of a lifted object? And that is a totally acceptable way of doing it. And that's, again, meter out. Okay? There's another way of doing this, and that's the use of a counterbalance valve. Okay, so let's put a counterbalance valve on something we want to go ahead and do a controlled descent of. Here's our lifted weight. And here's our counterbalance valve. And there it is. Here's P. Here's T. Now I want you to take an extremely, extremely close look at this counterbalance valve. Because, what I'm going to do is I'm going to go ahead and scratch out the meter out arrangement and stick in a sequence valve here and see if you can notice the difference. And there you go. Here on the right side is our counterbalance valve. Here on the left side is a sequence valve. And you might be like, oh gosh, they look astoundingly similar. And you're absolutely correct. And this is where location, 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 attention to details pays some serious dividends. Okay, since we already know the sequence valve, let's discuss what a counterbalance valve is. It's normally closed. It's sensing pressure at its inlet. It's check valve bypassed. The problem is the sequence valve has all that. It's normally closed. It's sensing pressure at its inlet. It's check valve bypassed. It's almost like they're mirror images of each other up to this point. Location and the big one, orientation. Notice how the sequence valve is controlling pressure into that cylinder, in this particular case, as it extends. And it will not open until pressure at its inlet exceeds a certain value, at which point it will open and allow pressurized flow to enter here. Counterbalance valve is doing the exact opposite. Because check it out. There's T at this end. It's coming from the cap end. This flow here is going to try to go through a normally closed valve. It can't. It's going to try to go through the check valve. It can't. Until pressure at its inlet port exceeds a certain value, at which point it will open up and allow flow to go through. And you already see what's going on here. What a counterbalance valve is doing, it's allowing pressure to build up, basically a back pressure in there to support that load. Exactly the problem, solving the exact problem that hooking a lifted load in this particular case directly to T and it would just slam to the ground. The problem was that there is no pressure in that section. But basically what a counterbalance valve is doing, it's providing a little bit of back pressure to support that weight. And what it's doing, basically allows that pressure to build up, at which point it will open up and modulate, and if the pressure gets too low, it's going to close and then open up as the pressure builds up and then close, basically opening up and closing up, allowing the slow descent of this object. Okay? What is the check valve bypass in there for? Well, very similar to the case of a sequence valve. In the case of a sequence valve, we want to retract this guy. Basically, allows retraction of that particular cylinder without an interference in its operation. What's a counterbalance check valve doing? Well, it's allowing extension of the cylinder without interfering with its normal operation. Dig? So counterbalance valve and sequence valve, very easily to be confused because they have some of the same properties right here. Normally closed, sensing on the inlet, its check valve bypass, its location, and this guy right here, orientation, is the big one. Okay? So what I just described right here was called an internal counterbalance valve. The reason why it's called an internal is because of this internal pilot line right there. It's basically sensing pressure on its inlet. Okay? There's something else called an external counterbalance valve. As the name implies, it's sensing pressure somewhere else. And when I say somewhere else, you can think of that as a remote operation. So external counterbalance valve can also be called a remote counterbalance valve. Very similar to our internal counterbalance valve, but it's got some added functionality, which I'll describe right here. Okay, so on the left here, we've drawn our external counterbalance valve, and on the right is our internal counterbalance valve, and we're going to see how these guys react differently. It's still the same thing. It's still normally closed. It's checking pressure in this particular case via a remote. I'm talking about this guy over there. It's still check valve bypassed. It's still got the same location and orientation as our internal counterbalance valve, but look at the application it's used for. So this is our roadkill roll-up factory. What we do, take all the roadkill, chuck them into a pit, and we smash them into little fruit roll-ups or roadkill roll-ups for the kids in school. And what this is implying here is our smasher, this thing right here, is very, very heavy. So obviously we want to do a controlled descent of our smasher. But as it moves through our roadkill, we're going to, it's going to turn it into kind of like a pulpy goo, you know, as we press down on it. But we want to really smash it, so we're going to be moving through it and basically compressing it down, okay, into that viscous roll-up substance. You know what I'm talking about, okay? So the advantage of an external counterbalance valve in this particular case right here is the fact that not only is it allowing the controlled descent of a lifted object, you'll see in a little bit as we describe the application of it, what it's doing, it's allowing us to use this weight to our advantage for an application like this when we want to crush something. Not only will we have the force of the induced by the pressure on that cap end, we can also use the force of this object to crush whatever we're crushing, okay? So whereas previously we're just trying to just get that weight down safely, now what we're trying to do is get the weight down safely. Not only do we want to get down safely, but at a certain point we want to start using the weight. And you'll see what's going to go on here. Okay, so we are in a situation where it's normally closed. It's checking pressure where? Right here. Okay? And now some of you guys might freak out. You'd be like, wait a second. That does not make sense. How is this going to control the descent of this incredibly heavy smasher? Because as soon as I put pressure in here, I'm going to push down on that thing, and it's just going to flow right through. Well, it can't, because there is a pressure relief, counterbalance valve in the way. But you're like, no, wait a second. Because there's pressure in there at its remote port, it's going to tell it to open up, and it's just going to go through. And the answer is still no, it's not going to. The reason why that will not open up in an uncontrolled fashion is because of cavitation. And think about this. If this cylinder were to suddenly run away, basically the weight drops it, because it's suddenly allowing fluid to flow that way. What happens to the pressure right here? Well, if it was to suddenly peel away from that pressurized fluid, what happens there? It's a cavitation event. Basically, it's reduced to its atmospheric pressure. Think about that. It's just ripping itself away. The cap is just ripping itself away from that fluid. What happens there? The pressure is dramatically reduced at this port, and it closes, because that is exactly what a counterbalance valve does. It's sensing pressure. In this particular case, an external counterbalance valve. It's sensing pressure in an external section, and if it suddenly drops too low, it's going to close it, because that's implying, hey, I'm starting to run away. It closes it, allows our back pressure to hold that object up, because again, it's closed. There's nowhere for this fluid to go. It can't go through the check valve either. Okay, and then pressure starts building up again here. What that external line is basically saying, it has to have pressure in the P line. Basically, the only way this extends is if you are putting pressure into this, okay? So that is kind of how it's controlling the descent of the object. But now, watch what happens here. Let's say we are now at the limits of travel. Not the limits of travel, close to the limits of travel. We're really bearing down on this thing. Basically, what that's implying is, I gotta draw my diagram better here. Our roadkill goo here is basically kind of holding it up at this point, but we want to mash it down. What that's implying is this thing's not going to run away anymore. Okay? So if it's not going to run away anymore, might as well put full pressure into here. What does full pressure do? It completely opens our counterbalance valve, because there is significant pressure in here. And now full pressure is acting on that rod, which is acting on the weight. Oh, by the way, the weight is pulling down too. Okay? So it's one of those double things at this point. We had a controlled descent until it's in a semi-supported condition, and it's not going to do this cavitation event, which we just talked about here. But now it's basically at the limits of its travel. It is going to have strong compression at the limits of pressure, at the limits of travel, because there is no back pressure holding it up here. It's fully open and fully dumping that to the tank. Okay, it's the same thing as an internal counterbalance valve, except it's sensing pressure from a different location. And basically, the only thing that changes on this guy is basically it's a strong compression at the limits of travel. It's allowing that full pressure to hit that cap end, and in this case, use a weight. Okay, so that was the fourth of our 6 major pressure control valves. So let's go ahead and clear the slate a little bit and go on to our 5th, and that is known as an unloading valve. Okay, so if I was to ask you, how do I speed up the extension of a particular cylinder? And your probably first reaction at this point is to say, I would do a regenerative extension arrangement, whereby pressurized flow enters both the cap and rod end, and because of the area imbalance, this versus this cylinder will extend still, but that flow from the rod end is rerouted to the cap end, allowing us to extend at an incredibly fast rate, albeit weakly, because of that. That's what the area imbalance is, and that pressurized flow is acting just on that area. So that is a means of a fast extension, is regenerative extension. There is another method, and that is typically using an unloading valve. Okay, so find for me, if you will, between these two valves, the pressure relief valve. And the pressure relief valve is right here. You might be saying, hey, wait a second, what about this guy right here? Because Jim has told me a pressure relief valve is normally closed next to a pump. This guy right there, excuse me, this guy right here is normally closed, and it seems to be next to a pump. However, there is a difference between these two guys. Notice this line right here. A pressure relief valve is an internal means of sensing pressure. An unloading valve is almost the same as a pressure relief valve, even though I've drawn this one on its side, except it's got an external means of sensing pressure. Okay, what is this system that I just drawn here? What will this do? Okay, before we do this here, these are two different types of pumps. This guy is high flow, low pressure. This guy is low flow, high pressure. Hence the name high, low system. Okay? Why on earth are we using two pumps? Well, because check this out. High flow, low pressure pump is cheap. Low flow, high pressure pump is cheap. You know what costs money? High flow, high pressure. Okay? So what we do is use the advantage of the fact that these are little money. We don't have to buy one of these guys right here. Okay? So what we do, it's something very similar. The ultimate result is very similar to our regenerative extension. Because remember, regenerative extension extends fast but weakly. It's fast and weak. But when we switch over to a straight through condition, where it's P2T, that's slow and strong. In a high-low system, we don't use a regenerative extension valve. We use an unloading valve to accomplish this exact same thing. So rather than replacing this valve right here with a 4-position with a regenerative extension or some pilot pressure that's sensing on it, what we use is an unloading valve. And how it does it is as follows. Basically, in low pressure conditions, both pumps let's say we are in the straight through condition. Both pumps are providing flow. At this point, this check valve, it pushes through, and because we're in the straight through position, we are extending that cylinder. At what pressure are we extending it? The maximum we could ever get to is that low, is the limit of the low pressure pump. Okay? The reason why is because this, as we remember, each pump has a pump curve. As increasing pressure, flow goes down. That's flow right there. So at some point, this pump is be like, dude, I can't handle it anymore. You got to pick it up from here. And that's exactly how the unloading valve works. Basically, the unloading valve is sensing pressure right here. Sometimes, hopefully, preferably before that pump dies out. Basically, all that does is when pressure reaches the limits of this particular pump's pump curve, this guy opens up and allows this thing to dump. Okay? What happens to the high pressure? It can't go back through the pump because that would be a problem. It couldn't, spin this pump backwards, acting almost like a gear motor in that particular case. So this check valve is critical to the operation of a unloading valve high-low system. Okay, basically it's allowing, so for a certain portion of this cylinder's extension, it's allowing it to extend fast and weak, very similar to a regenerative extension, at which point this pump dumps to tank, and then it goes slow and strong because it's using only this pump. And those pumps are basically running in tandem at the very beginning. They're running simultaneously, combining flows up to a certain pressure requirement at which the high flow, low pressure pump can't make it up. And at that point, it drops out, and the low flow, high pressure takes over, and we are in the slow and strong extension. Okay, so an unloading valve, that is a super good application, high-low system. There are other applications which you will see unloading valves, which I'm going to go ahead and clean this up and draw one right here. So what about this application for an unloading valve here? Here we have a unloading valve. Basically, a pump is going to pump, 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 pump. It's going to push through that check valve, and it's going to go into the system. I forgot to draw something here real quick. And if this solenoid A, because remember we're drawing our schematics in an unenergized state, if that solenoid A is energized, in which position is this two-position valve in? It's in that straight through position, and the accumulator right here is charging up, charging up, charging up, and basically at some point there is a pressure that is sensed by the unloading valve via its remote port that says, hey, that's enough. There's enough pressure in this system that I can go ahead and dump that flow of the pump at low pressure to the tank. And because of this check valve here, that is not going to bleed out. Pretty cool, huh? So an unloading valve in this particular case is just saving us some energy. What we're doing is we're accumulating energy appropriately enough in our accumulator, at which point there's enough energy to run our system, whatever it may be. The pump can take a break. It's basically just dumping at low pressure to the tank and not heating up or anything like that, the fluid. And as long as solenoid A is remaining energized, the accumulator is there to run the system, at which point it runs it for a couple times maybe, and then the pressure drops. Okay, hey, we need more pressure, we need more flow. What's happening here is that pressure signal goes away, our unloading valve goes back to its normally closed state, and our pump can start providing pressurized flow again into our accumulator. Pretty cool. One quick note about this guy here, this last one here. Let me add something into this diagram here and see if you can see the error. Okay, I've very subtly added a difference to our high-low system there. And it should be pretty obvious as to what that deadly error is. Right there. That is not the place for a check valve. Why? Well, it's right next to the pressure relief valve. What's happening there is the unloading valve has got this side. It's got that side covered. So if pressure at this point ever goes to above a certain value, it's got that side covered. It can safely handle that. What happens here? Basically, pressure is going to build up and build up and build up, and some line's going to break, or your pump's going to break, because there's no way pressurized flow can go through there. So if you ever see a diagram in maybe a textbook that we might be using with a check valve in there, you need to go ahead and make sure that that check valve is not in there. Okay? So that would be a very deadly error. Okay, so that was our unloading valve. Again, what is it used for in a high-low system? Fast and weak extension, using our combination of our high flow and low pressure pump with our low flow and high pressure pump, and that at a certain point it's making a decision upon an externally line here, at which point just the low flow and high pressure take over, because it's unloaded the high flow and low pressure pump, and it's the slow and strong extension. Very similar to our regenerative extension, except we're using a pressure control valve as opposed to a regenerative extension valve. Next application of our unloading valve was our accumulator. We're basically just charging up our accumulator to a certain point at which the pump is unloaded and then running off the accumulator until a certain point, and then allows itself to go ahead and charge back up. Okay, so the last and sixth of our pressure control valve is the brake valve. And the brake valve, we're just going to touch on it super briefly. Where there's smoke, there's fire. If you see a hydraulic motor and a valve, a pressure control valve that looks something like this, I can pretty much guarantee that that valve is a brake valve. So what's the difference? What's the major characteristics about this? Well, it's the only one with two pilot lines. It's got this one hooked on its inlet. It's got this external pilot line. Additionally, it's the only valve next to a hydraulic motor. Okay, as the name implies, a brake valve is designed to basically make sure the hydraulic motor just doesn't run away from you. Okay, so how it does this, a hydraulic motor is basically, a particular example is a gear motor, very similar to a gear pump. Now, if you could imagine if there was pressurized flow coming into one side and there was nothing on the other side, it would just kind of spin out of control. So that's exactly what a brake valve is doing. It's basically providing some back pressure by having a normally closed valve. Some back pressure on it against the pressure that's coming in on the inlet side. Okay, so basically having some back pressure in there allows the pressure to build up, and then because they're going in opposition to each other. And then when that valve opens up, so it's slowly building that pressure in there until finally it opens up, slowly opens up, and it's slowly starting up. It's not just going to suddenly ramp up and go crazy on you. Okay, so it's that nice and controlled means of controlling the speed of a hydraulic motor. Okay, so that was kind of on the remote side there. So what it's doing is, again, is allowing, once keeping that closed until there's pressure there, pressure on the inlet side, and then allowing it to open is making sure, because if there is no passageway through there, it's just not dumping to tank. I don't know if I'm doing a really good job explaining this. It's just not dumping to tank at this point. There is back pressure there, and it's not just going to suddenly go crazy. Okay, so that's what that remote is doing there. It's then, once pressure gets to a certain point there, because it's going in opposition, it's going to open up. Now, what's the inlet? And now it's open and it's running and it's just going fine. But all of a sudden, let's say it starts running away on us. That's where our inlet pilot port makes a difference, because if our inlet starts running away on us here, excuse me, if it's running away, it's going to travel. The pressure is going to travel through the inlet to close that valve again. Okay. Okay, I've got to come up with a better way to explain this, because what I'm talking about is I need to make a clear distinction here. The outlet of the motor is it's sensing the inlet. The inlet pilot port of the brake valve is sensing the pressure of the outlet of the motor. Does that make sense? Okay. So if the motor is running away, it's going too fast. Basically, that pressure on the inlet is going to the outlet, which is now the inlet of the brake valve. And basically, if that exceeds a certain value, our valve closes again. Okay, hopefully that makes a lot more sense. What I was trying to refer to is the inlet of the counterbalance valve, the inlet pilot port. It's sensing pressure, the outlet of the hydraulic motor. Hopefully that makes sense. Long story short, let's just put it this way. If you see a hydraulic motor and you see a valve with two pilot ports coming off it, it is a brake valve. Okay? So hopefully that is clear as mud right now. But what I want you to understand is that we have completed our pressure control valves. We did our pressure relief valve. We did our pressure reducing valve. We did our sequence valve, which for some reason is mysteriously missing. We talked about internal counterbalance valves. Its close cousin, the external counterbalance valve. The fifth one, our unloading valve, used in two applications, the high and low system, and our accumulator charge-up system. And finally, our sixth one, the brake valve. Okay, we're going to go into some hydraulic fluid filtration and contamination controls in the next lectures.